Hello and welcome back, everybody. We continue our study of neighborhoods of 0 in topological vector spaces. And we prove the following lemma. Let X be a topological vector space, just like in the last lecture. And suppose that V is a neighborhood of 0 then the following is true. If you have a sequence, to be precise, an ascending sequence of real numbers, so R1 is greater than 0, is less than R2, and is less than R2 is less than R3, and so on. And the sequence tends to infinity as I tends to infinity. Then we can write X, our topological space X, as a union of sets R and V. So, proof. We pick an arbitrary X and we show that it is in this union, and then we will have shown that X is indeed this union over the sets R and V. So pick X, define a function f in the following way. Scalars alpha get multiplied by this fixed X. Well, let's write it this way. Alpha is sent to alpha X. I think this way is more clear. Now, this is a continuous function, and this means that the pre-image of the neighborhood V is open in the real numbers. And it contains 0 because 0, the scalar 0, gets mapped to 0 times x, which is 0, of course. And since V is a neighborhood of 0, we see that 0 is indeed in the pre-image of V. So this 0 is different from this 0, of course, and this one is in the pre-image of V. And now look, the pre-image of V is open and it contains 0. So if you pick a small enough ball around 0, the image of this small ball will still be in V. So one way to write this down is 1 over Rn. This Rn comes from the sequence here of numbers R that we defined in the statement of the theorem. This 1 over Rn is an element of V if you pick Rn big enough. But f of 1 over Rn is the same as 1 over Rn times x. Maybe let's write it this way, is the same as x divided by r to the n. And this now is in V. This means that x is an element of r to the n, Rn V. And this shows that every x is in a set Rnv, and this shows that all of x is in the union over the sets Rnv. And this concludes our proof. Thank you for watching. See you next time.